All right, hello everyone, and welcome to my channel. This is an educational channel where we try to focus in on various theories of everything and go into deep dives on them so you get the full picture and you can use these things in your own life. Make the paradigm yours and apply them to new and novel and different questions that you have in your life that could also benefit others. So today is our 350th video on the reciprocal system of theory, and this is a theory that was first arrived at by Dewey B. Larson way back almost 100 years ago. And he passed away in 1990 after 60 years or so working on his problems. And then a few people have picked up the mantle and have attempted to push forward the theory and move it into new areas, revise some of the kinks. And one of them was Dr. Bruce Peret, who also passed away back in 2020. But before that, he did some great work in putting out what he called RS2, along with Dr. KVK Nehru. And the RS2 is a re-evaluation of the reciprocal system. So taking, the high points and preserving them, while some of the sticking points, revising those, all the while remaining in the spirit of Larson's reciprocal system, which is the basic gist of the reciprocal system is that the universe is made not out of matter, not out of energy, not out of the fundamental forces. The universe is made out of motion, and is made out of a specific kind of motion called scalar motion, which is a more generalized kind of motion than the normal vectorial motion of velocity that we know of, where the motion has a direction. A scalar motion is a motion that has a magnitude, but it has no specific direction. You can envision this using a balloon with dots on it. When you blow up the balloon, all the dots are moving away from each other, and but they're not moving in any specific direction. That is a scalar motion. And you might say, well, that seems rather abstruse, but this is actually a motion that was observed by the Hubble telescope, as all of the distant galaxies are participating in this kind of motion. They're all moving away from each other. And as long as we don't want to put ourselves in the position of being at the center of the universe, that basically means that our galaxy is also participating in this galactic recession. All of the galaxies are moving away from each other in no particular direction, and the farther away we are, the faster we are moving away from each other. And if you put that in the reverse also, if you suck in the balloon rather than blow out the balloon, all the spots on the balloon are moving toward each other. And that is analogous to gravitation. So gravitation is a motion, a scalar motion like that as well. So it is somewhat of a mystery why legacy science hasn't focused on this kind of a scalar motion as being more fundamental than it is. But for whatever reason, Larson has picked that up, and so his first postulate says that the universe is composed entirely of motion, particularly scalar motion. And then it comes in 3 dimensions, and in discrete units, and with 2 reciprocal aspects, space and time. So basically, motion is the relationship between space and time. And that creates a generalized reciprocal relationship between space and time. Space and time are not separate. They only work together in motion. And space and time, being reciprocals of each other, have the same qualities. One of them is that they are three-dimensional. We can easily see this with space, generally X, Y, Z coordinates, 3 dimensions of space, but we don't generally recognize 3 dimensions of time. But that's what Larson calls coordinate time. And then there's also the clock aspects. That's a scalar motion. The clock is always getting later and later and later and later. And that is a motion that has a magnitude, but it has no specific direction. The time is not getting later in any particular direction. And then the counterpart to that would be clock space, which is a concept we're not as familiar with, but this is basically that space is getting farther and farther and farther apart, like the dots on an expanding balloon, and like the distant galaxies. So that is clock space. All the space is getting farther and farther and farther apart. You can think of this as, an expansion of space itself. And, the motions do not have a direction until you assign a reference point. When you determine that arbitrarily determine that one of the dots on the balloon is actually stationary, when you make that abstraction, where you make that arbitrary call that this one is stationary, then all of a sudden the directions start to appear. And you can determine the directions from that particular dot to all the other dots. And that's where you end up getting concepts not only like direction in motion, but also force fields, gravitational field, also magnetic and electric fields. And then also space and time come in only discrete units, meaning that there is a minimum unit of space and a minimum unit of time. And you have to have a full unit in order to have those things. You can't just get by with a fractional unit of space. You have to have a full unit. And it turns out that the full unit is 4.56 times 10 to the minus 8 meters. And I think that's like a 2/millionth of an inch or something like that. That could be very wrong. It's 20/millionth of a meter. So something like 1/2 millionth of an inch. And then you also have the discrete unit of time, which is much smaller, which is 1.52 times 10 to the minus 16 seconds, meaning that you can fit 6.576 quadrillion of them into 1 second. So that's a quadrillion is a 1,000 trillion. So it's a million billion, and it's a billion million. It's a trillion thousand. So it's a big number. Anyway, if you have 1 unit of space in 1 unit of time, you have the speed of light. And so the speed of light is what Larson calls unit speed. 1/1 equals 1. And this is the place, this is the center point of this universe. And it's what you call the 0 point, the natural, the progression of the natural reference system, or the natural reference point, the null point, the state of rest, the origin, the ether. And this is the place where time actually equals space, as 1. Everywhere else, there is the ratio of time to space is different. It could be 2 to 1, it could be 2 to 3 to 1, or it could be 1 to 2, or it could be 1 to 3, or 1 to 4. But it's always integers, and that is the discrete unit postulate. And so basically, motion is a fraction with time or space as the numerator and space or time as the denominator. Speed, the most basic kind of motion, that is space over time. The car is going 10 miles per hour. 10 miles of space, 1 hour of time. Energy, that would be time over space. Took me 1 hour to push that thing half a mile. 1 hour of space, 1 hour of time, 1 hour of time in 1/2 mile of space. Time over space, energy. Acceleration, I dropped the rock out the window and it fell to the ground at 32 feet per second squared. Time, space over time to the second power. 32 feet of space in 1 second per second of time. Space over time squared. Acceleration. And so on and so forth. There are many other things that we could get into, but that is just a short discussion of the how the reciprocal system works. And now we're going to get into part 2 of reading this paper here from Dr. Bruce Peret called Quantum Pi. And this is the 5th paper in his series of tutorials on RS2, the reciprocal system 2, his re-evaluation of the reciprocal system. And here he's basically showing this discrete unit postulate in action, and that many of the things that are involved in this discrete units, they really, when you break them down, they are pixelated and they are rigid and continuous and discontinuous. But because the units are so small, it looks smooth, curvy, and therefore pi looks like pi, 3.1415925, but really pi actually equals 4, which is the ratio of the perimeter of a square to the diameter of that square, as opposed to pi, which is the ratio of the circumference of a circle with the diameter of the circle. So when you change from a rational pi for a circle to pi equals 4, you're changing from a circle to a square. And Peret is saying that when you get right down to it at the smallest level, you're talking about squares and not circles. And so we're going to take over here at this point where he's talking about pixels. Pixels are treated as a unit in the sense that a blue pixel will be all blue. You cannot start with red on one side and end up with blue on the other side in the same pixel. The entire pixel will always be the same color and intensity across its surface area. This is analogous to Larson's discrete unit postulate. You can only change color after you exit one pixel and start another. Angled lines and curves drawn with pixels therefore appear jagged if you look at them closely enough, with a magnifying glass or a microscope or whatever. Stair steps is this section. The rectangles are what the computer actually displays in pixels to make the black line that is seen on the monitor. It is optical trickery. And again, I was also using that same the analogy of the cartoon, just like that. I guess that would be in time rather than in space, where you are showing still photos or still pictures, but you're showing them in rapid succession. And so it appears as if there's a continuous motion going on. But if you slow down the motion, you will see that it's just one picture after another that are slightly different. And so that is the same kind of illusion of the universe, that the universe is moving so fast that it appears to be continuous, but it is actually discrete. Consider the same situation in nature. The observable, measurable universe is also pixelated. Because of the reciprocal system, because of the reciprocal system's discrete unit postulate and the absolute scaled orthogonal Euclidean projection. It is a grid of cubes. We just call it quantized rather than pixelated. Now consider what happens if you try to draw a circle on a computer monitor that has a radius of 1 pixel. You get a 2 by 2 square with a circumference of 8 units, a diameter of 2 units, and pi, the ratio of circumference to diameter, is actually 8 over 2 equals 4, not 3.159265, due to pixelation. Programmers that dealt with the early computer graphics worked at pixel level and knew that the perimeter of a pixelated circle is 4 times its diameter. This had to be accounted for when a user tried to pick a location on a circle because it was approximated with a light pen. You could select the pixel approximating the circle near where the mathematical circle should be, but seldom exactly on it. Now he kind of goes through a chart here, which unfortunately didn't really transpose to my computer the same way that it was appearing on the screen. But, it's just showing that, if you're, okay, here we go. Take that unit square representing a pixelated circle and increase the radius to 2 or 3. You get a series of squares. Since the curvature of the real circle, real in quotes, the curvature of the real circle is still too steep to clip any of the corners. As the diameter increases, clipping occurs as indicated by the gray squares in radius equals 4, resulting in a decreasing ratio of circular to square area that appears completely lost my place. As the ratio increases, as the diameter increases, clipping occurs as indicated by the gray squares in radius equals 4, resulting in a descending ratio of circular to square area that approaches the accepted value for pi as the radius approaches infinity. So as your radius gets larger and larger and larger, the values get closer and closer and closer to pi. never reaching it. Okay, so the radius starts at 4, one at a diameter of 2. You know, 1 quantum square. But as the radius increases, the value of pi decreases from 4 down to an idealized level of pi, which is never realized. You would only get to pi if your radius was infinite. The clipped pixels are those that are entirely outside the circular area. So as you get larger and larger, you know, the circle there will be certain pixels. You know, if you have a square, and you know, say you have a 10 by 10 square, you know, you have 10 by 10 each. The circle will eventually get to a point where there are certain squares that are completely outside of the circle, and you can clip those off, and that's how the value of pi will start to decrease. And he has a chart explaining that. Let's see here. The clipped pixels are those that are entirely outside the circular area. But note that the radial to square area changes with radius. The perimeter does not. Even if, when following the jagged path around the clipped boxes, the perimeter is always 6r, or 2 pi r, where pi equals 4. Pixels, square area. So this is just his chart, you know, showing how eventually these things start to approach pi. If you've got, it looks like if you have a 10 by 10 grid, then pi is still 3.64, and if you got a 12 by 12, you're down to, well, I don't know. It looks like it's going up, actually. If you got a 14 by 14 grid, you're 3.51. 16 by 16 is 3.50, and so on and so forth. So eventually, once you get up to 300, you are down to 3.154. So you're getting pretty close. And by the time you're up to a radius of 500, you're down to 3.149. So you're getting closer and closer, but you would have to get all the way up to infinite before you got down to 3.1415965 with a radius of 1,000, with a diameter of 1,000, you're at 3.14554,400. Okay. It is this knowledge of pixelated or discrete circles that provides a reciprocal system understanding of Miles Mathis's pi equals 4 concept. By assuming that the smallest quantity is a single discrete unit rather than the smallest quantity approaching nothing, limit of 0, you are quantizing the system into a square. Pixelated components where there is no such thing as a curve, only an approximation of a curve made with stair-stepped lines of a fixed unit-sized width. But if that width is very, very small, it can very closely approximate a curve. That stair-stepping, or, jagged lines, like a stair, that stair-stepping adds the extra distance to the perimeter to bring it up to 4.0, bring pi up to 4.0. So there are actually three different concepts for this ratio, as we refer to as pi. The analog, which is circumference over diameter, 3.14159. In all cases, this is called by Peret the yin aspect. This is the mathematical value that only exists in mathematics, not in nature. Then we have the quantized, the perimeter over diameter equals 4.00 in all cases. This is the yang aspect. Due to the discrete unit, smallest quantity of 1, this is the value found in the three-dimensional spatial coordinate system of nature. So in coordinate space. And then the transitional area over radius squared is from 4 down to, limiting to 3.14159 as radius goes to infinity. This is a range of values dependent upon radius, but note that in nature all quantities are finite. There are no infinities, hence the mathematical value for pi can never be reached, since the radius or area will always be limited. Okay, I think we're going to stop it right there and get ready to start up, and I don't know if we're going to get through this paper tomorrow, but yes, I believe we will. And so we're going to stop it right here, and we'll be back with the third installment of this paper tomorrow. So just hang in there. If you don't get it, that's how you study the reciprocal system, basically, is you suspend disbelief and you just let it wash over you, and then you scrutinize the ideas over time. But if you come to it with a naysayer's attitude that, oh, I'm going to just pick holes in this, then it's probably not for you in the first place, because you need to have a more open mind to embrace new ideas that are unfamiliar. And that's what we're trying to do here. So, I'm reading these. I've read some of these articles multiple times, and I'm still confused by some of them. So, but I feel like I'm making great progress with the reciprocal system. I understand it a hell of a lot better than I did 12 months ago. And I've been studying it for 20 years, so I'm still making great progress. Now, I came from a very low place. I'm a liberal arts guy. So, I'm good at math, but I'm not trained in any of these subjects other than like high school. I took astronomy in college. I guess I did take 3 semesters of calculus, but I never learned anything when I took those. And I think I did take a college physics course, but basically I'm a liberal arts person. I'm a history guy. So actually that probably worked to my benefit, because science people seem to be about the last people that will let go of their paradigm and try to embrace new ideas. They're so committed to their old ideas that they don't have an open mind about finding anything new. But if you look at the history of science, you'll recognize that every last one of the major innovations in science has come from outsiders to the field. The only major revolutions come from outsiders. The insiders can provide you with, you know, little innovations, but the revolutionary changes come from outsiders. And so that is my advice from a historian to a scientist, is that if you want to make a revolutionary change, you better start looking outside your field. Okay, thanks for tuning in today, and I hope to see you tomorrow. Have a great